Let's take a quick look at how confidence intervals actually work. We're going to build a sample drawn from some normal population with a mean that we know, otherwise I wouldn't be able to generate it, but as soon as I've generated the sample, we'll forget that we know what the mean is. And that has a standard deviation of 2. We're going to use a seed of 0, setting this for replicability so that whenever you try it, you'll get the same results that I do. We want the sample to be of size 17. The population mean, as I said, will be -3. The standard deviation will be 2, and we're drawing those from a normal distribution with parameters mu and sigma. We're drawing 17 of them. So what does my sample look like? Well, I got these 17 numbers here. It's a little bit hard to see if this behaves like what I would expect it to, so one way in which I can get more information is by plotting the histogram. Alright, so it's normalish. I'm not seeing very well. Let me see what happens if I bring this up a little bit. Am I going to see something that's a little... It looks a little bit normalish. It seems to be perhaps too many points in this bin, but you know, it's an accident of the sample that I've selected here. I'm okay with this. We can compute the sample mean. It will just be given by this expression here, mean of the vector x. And I get -2.8, which is indeed not too far from the -3, which is the true mean of the population from which these samples are selected. So how do we build a confidence interval? You'll remember we know that the underlying population is normal, which means that we use critical values from the standard normal distribution, alpha over 2 and 1 minus alpha over 2 for the lower bound and the upper bound. Well, does this really make sense? It would give me -3.75 and -1.85. Here we're building a confidence interval for the population mean. But what are all these numbers? We know what mean at x is. That's the point estimate, the sample mean. What about the rest of the expression here? I have q norm alpha divided by 2, sigma, which is the standard deviation, which I know, divided by square root of n, square root of the sample size, which I know as well. What is this thing here really? Is it truly the critical value? Let's actually compute it. We'll see that we have -1.96. It is indeed the critical value, but it's the critical value in the lower end of the standard normal distribution. The positive one is this one here. So Q norm is not defined the same way in R as it is defined in your tables. This confidence interval that I found, this 95% confidence interval, it goes from -3 to -1.85. That's based on the sample that we drew from the original population. And you'll notice that -3, the true mean, which we don't typically know whenever we look at a sample, but here we do know it, is indeed found within confidence interval. You could confirm that this is indeed the case. You can ask whether the lower bound is smaller than mu and mu is smaller than the upper bound. Is it actually found in the interval? And you get an answer of true. It is indeed found in the interval. Now, I spent a fair amount of time explaining to you what a confidence interval was and what the 95% confidence interval actually means. It doesn't mean that I'm 95% certain that the true mean is in the interval. It means that if I was to repeat the procedure multiple times over with samples of the same size, 95% of the time the true mean would be found within the confidence interval that I had built. So we will repeat this process multiple times. We'll do it 1,000 times, in fact. And we'll verify how often mu of the true mean, -3, actually falls in the confidence intervals that we've built. So what I'm going to do is I'm going to use the code here that allowed me to build one confidence interval for a given sample, and I'm going to iterate through a variety of samples, build the confidence interval every time, and verify how often the true mean was within the confidence intervals that I built. So again, for replicability, we'll set the seed to be equal to 0, so you can run and get the same results. We have 17 samples. We draw them from a normal distribution with the population mean -3, mu. We'll use a standard deviation of 2, great. we're going to build 95% confidence intervals. So we pick a confidence level, a significance level of 5. And I'm going to go through this process 1,000 times. I'll build 1,000 intervals. If it is indeed the case that I've built a 95% confidence interval, I would expect that in 95% of the cases, the true mean should be within the confidence interval that I have built. So out of 1,000 iterations, I would expect it to be in the confidence interval about 950 times. A little bit more, a little less. There'll be some noise, some randomness associated with this, but in that ballpark. The next few steps I'm going to use to initialize my objects in R. So I'm going to have one vector that will determine for each of the steps whether mu, the true value of mu, which I know in this case is in fact in the confidence interval. And I'm going to initialize a vector of sample means. I want to keep track of my sample means for each iteration so that I can give you a histogram of the sample means at the end of the process. So what am I going to do here? I'm going to build a loop. What does the loop do? It's going to go through my 1,000 iterations, and in each iteration it's going to draw a new sample from the population with mean -3 and standard deviation 2, and it is going to build, based on that sample, the 95% confidence interval. It will use the sample mean for that specific sample, which it will keep in memory, and then the rest of the computation, the radius of the confidence interval will not change. It's always the same thing at every step of the process. If I wanted to make the code more efficient, I could have computed this radius, put it in memory, just call on it. That's not that difficult of a computation memory-wise, so I'll just keep on computing the radius for every iteration, but it's always going to be the same quantity here. And at the end of the process, I will ask the question, is the true mean -3 actually found inside of the confidence interval that I just built? Run the loop. See, it doesn't take that long to run. And now I'm going to look at the proportion of the times when mu was inside the actual confidence interval. So table is going to give me a frequency count for this variable. I'll divide it by the number of iterations to get a percentage. So what I get here is that in 94.5% of the cases, so 945 times out of 1,000, the true mean was inside the confidence interval that I built, and in 5.5% of the case, it wasn't. See, not exactly 95%, not exactly 5%, but that's what randomness is. You can't ever guarantee, if you flip a coin 1,000 times, that you're going to be getting 500 heads and 500 tails. And if you wanted to take a quick look at the histogram of the sample means. Now, before I do this, notice that the histogram of the original sample of 17 observations sort of ranged from -7 to 2. There were some values fairly far from the -3. Not that far, because the standard deviation is 2, and you would expect about 95% of the observations to be between -5 and 1, the mean plus or minus twice the standard deviation, so that's not completely surprising. Now let's take a look at the histogram of the actual sample means, one for each of the iterations that I ran. Oh, and I get a much tighter histogram. See the frequency count here, I'm talking about fairly large numbers. So I get something that almost looks normal. In fact, I could probably get a curve that looks even more like a normal distribution by increasing the number of breaks. Now, what would you expect to see if you changed n alpha or capital N, the number of iterations? Well, you have a chance. You can go and play with these parameter values here and see what differences this provides, both on the histogram, and you compute the number of times you fall within the confidence interval. So we've done this knowing what the underlying population was. It was a normal population with a given mean that we were trying to estimate and a standard deviation that was known. Now, if we draw from a normal population where the mean isn't known, this is what we're trying to estimate, and the variance is also not known, well, what do we do in that case? So I'm going to use the same sample as what we've worked with in the first question. It's still going to come from a normal distribution, but this time we don't know what the actual variance is. To generate the numbers, we'll have to put in a number, and we'll put in the same number as before. The sample we get is going to be the same sample, but This time we do not know what the true sigma was. We can still compute the sample mean, hasn't changed. The sample variance, we call the var function in R, and it gives me 4.28. That's the variance. If I wanted to know what the standard deviation was, call SD 2.07. So the sample standard deviation is close to the true standard deviation that was used to generate the sample, but the risk of repeating myself, we don't actually technically know what that standard deviation is. So I'm just looking at this and I'm saying it looks like it's 2.07. You compute the confidence intervals using the same principle as before, the one difference being that this time, since you don't know what the standard deviation is, you have to estimate the standard deviation using the sample variance or the sample standard deviation. So I could have used here SD at x instead of square root of the variance of x. The rest of the formula is the same. I estimate the confidence interval by first computing the sample mean, that's the center of my interval, that's my point estimate, and then the radius, the center to the lower bound or the upper bound, is the sample standard deviation divided by the square root of the sample size. And because I'm estimating the standard deviation, I have to use student's t-distribution with n-1 degrees of freedom, and I'm looking for the critical point of that distribution, the alpha divided by 2 point in both directions. If I'm looking for a 95% confidence interval, my significance level is at 5%, and then I can compute a lower bound and an upper bound, get the following confidence interval. Compare that, minus 3.869 minus 1.740, to the confidence interval we got when we computed knowing what the standard deviation was. It's the same sample in both cases, but our prior knowledge of the situation actually changes the tightness of the confidence interval. The confidence interval is tighter when we do know the standard deviation. We have more information. We are more confident. So the confidence interval is tighter, and when we don't know the standard deviation, the confidence interval is wider. So the product here of the critical value of the student t-distribution with n-1 degrees of freedom, 16 in this case, times the sample standard deviation, that's going to be larger than the product of the true standard deviation times the critical value of the standard normal distribution, alpha divided by 2, in general. There might be exceptions, but in general that's going to be the case. And sure enough, even when we do not know the standard deviation, when we have to estimate it from the sample, the true value of the population mean, minus 3, was found within the confidence interval. This is something you can confirm by determining if mu was above the lower bound and below the upper bound. So if you do this 1,000 times, how often do you think mu is going to fall in the confidence interval? It is going to be the same piece of code as before, the one difference being that I need to use the critical value of the student t-distribution with 16 degrees of freedom, n-1, at alpha divided by 2. I compute how often the true population mean is inside the confidence interval. I get, in this case, exactly 950 times, and 50 occasions it will be outside. Now, it's an accident that the number of times the confidence interval contains the true population mean is exactly 950, which is exactly 95% of the time. There could have been some variation as well.